And the goal of today's talk will be to give a definition of what is a high-dimensional expander.
Can I pass it?
So let me begin by just recalling what Ellen taught us in this class on expander graphs. And let's say we're in the setting where we have a graph, simple, connected, finite, k-regular. And we saw that for any such graph, it makes sense to associate an adjacency operator, and then denote it by A, but I prefer to use the letter T for some reason. And there are associated eigenvalues. So again, I slightly alter the notation of Alain Vallet. So I start my indexation with lambda 1. He started with lambda 0 being the trivial, but for me lambda 1 is the trivial. And we've seen certain properties. For instance, lambda 2 is strictly smaller than d if and only if x is connected.
So D is K, Shai.
D is k, yeah. Thank you. In case we have and in his talk, he mentioned that there was another nice operator that one can associate to the graph, the Laplacian. And I do want to, so on the one hand, I do want to define the Laplacian, and then second later, you will see that you don't really need to know what is the Laplacian if you know the adjacency operator, because you can read one from the other one. But the Laplacian is basically a composition of two operators, one that takes a function on the vertices to functions on the edges. And there is, to define it, there is actually need to fix some orientation on the edges. Any orientation will do. And so this is the coboundary operator, and the boundary operator is well, it's the adjoint operator where say A plus is equal to B. And what happened when you compose first delta and then it's adjoint? So let's see. You start with a vertex.
Sorry, what's the name of the letter for the adjoint?
In fact, it's called
delta?
partial. Yeah.
Yeah, and then the other one?
Delta and del. Or
Oh,
delta and partial
Okay.
if you're
Okay.
technical. You can probably, maybe it's better to write. And so maybe a nice exercise, a not very hard one, would be to show that what you actually get when you compose them is just it's d times the trivial operator minus the adjacency operator. Because for any vertex, what you do is you first you want to put ones on all of the edges, and then you want to maybe this should have been minus a plus, and then you want to on each edge you get. Let's start with. If you have a 1 on one vertex, then you want to put 1 on all of the edges. And then this is delta, and then the partial will just give you 1 on all the neighbors. And here you will put minus 1 on all the neighbors. And here you'll get d, because you get d from all of the edges touching the vertex. And I don't want to corrupt the letter lambda to denote the eigenvalues of both the adjacency operator and the Laplacian. So I'll just denote by mu. So of course, by this identity, you see that any eigenvalue of t, d minus that eigenvalue will be an eigenvalue of the Laplacian. And the discrepancy or the gap between the largest and the second largest eigenvalue of the adjacency operator is the minimal non-zero eigenvalue of the Laplacian, and this is what is called the spectral gap of the graph. Okay, and so now we can maybe one more things I want to show you before. Okay, no, I'll give you the definition and I'll show you the definition. Okay, so the graph is called epsilon expander if the Cheeger constant, which is defined as the minimum among all the So this is equivalent to Helen's definition of the Cheeger constant. This is, maybe he denoted the edges going outside. So A is a set of vertices. And this denotes the edges with one vertex in A and another vertex in the complement. And you minimize over between the set and its complement because both of them have the same boundary. And X is called an epsilon spectral expander if the spectral gap is bigger than epsilon. But let me do just a tiny bit of manipulation. So this is the smallest eigenvalue except for the trivial one. And the trivial one has an eigenvector, the constant function. So I might as well run over all the functions which are orthogonal to the constant function and look at this quotient. And simple linear algebra should tell you that if the constant function is an eigenvector of the zero eigenfunction, is an eigenfunction of the zero eigenvalue, then when you minimize over all functions orthogonal to it, then this will be minimized by the eigenfunction of mu of x. And one more piece of manipulation because delta is the composition, because the Laplacian is a composition of delta and its adjoint, I can move the adjoint to the other side. And what I get is that this is the norm of f, the norm of delta f divided by the norm of f. Yes.
On the Cheeger constant, so the minimum in the, they are taking the minimum, like after you have the Laplacian, yeah, what's that?
This is the complement of a, so it's v minus a.
E minus a.
Yeah. I could have just asked for, I could have just asked, take the set whose size is at most half the size of the entire graph, and that would be the minimum, and then I can just write here a. I decided to write it like this because, well, this is how it's more easy to generalize this to higher dimension. Okay, and one final thing, so that we saw let's stop is the Cheeger-Boozer inequality, which tell us that the Cheeger constant is lower bounded by half the spectral gap and upper bounded by the square root of twice times the degree times the spectral gap. Okay, so this is what I wanted to remind you from graph theory. Now let's see how we can extend this to higher dimensions.
Could you read aloud what you've written actually in your formula? It is 1/2 mu of x on the left side.
Half of the spectral gap
Yeah, and on the right
is smaller equal than the Cheeger constant,
Yeah.
smaller equal than square root of 2 times the degree times the spectral gap.
2 times degree times spectrum.
Yeah. Okay. Okay, so now X will be a d-dimensional simplicial complex. I'll assume that it is pure, meaning that every maximal face is of dimension b. And I'll also, there is a technicality here with orientation, and one way to overcome it is to give an ordering on the vertices. So I order them in some arbitrary way. Ordering, this is, will take care of the orientation. So now, because of the ordering, because of the orientation, I want to say that whenever I have let's say, an I-dimensional face and an I+1 dimensional face, I can ask whether it contains it or whether there's an incidence. But I also want to record the orientation of the incidence. And so, okay, so xi will denote the I-dimensional faces of X, and for two faces, one of dimension I and another one dimension higher, define their incidence number the incidence number of the small face in the bigger face to be 0 if the big face does not contain the small face, and to be plus or minus 1 well, depending on it's in the other case where sigma is contained in tau, then I want the index of the vertex to determine whether I should say that this is of an incidence number of -1 or 1. This you can we'll see tomorrow that we can ignore incidence when we're working over F2, but then there are another set of problems that occur. Okay.
This is the vertex missing. Okay. Minus.
And again, one more thing, I want to define the degree function. So let's. Okay, so I'll talk with it in a second.
I didn't understand. You have this order V1 smaller to the Vn.
Yeah, I'm just
What's the next word? Order and then?
orientation.
Oh, ordering.
Yeah, it's ordering and orientation.
Okay, so any ordering is giving
Any
you
order, yeah. Usually, what's the correct thing to do is not to say to number the vertices, but to actually take faces with directions.
Yeah.
Above each face, like for each edge, you can take 2 edges, one in direction this one, the other one in the other direction, and then you want to make. So for an I face, you could have I factorial different directions, but you want to consider all of those who can be permuted by Linial permutation the same, and then you just record -1 on 1 of the orientation. So, and yeah, this is looks a bit unnatural, but it does the trick. And again, it's just something needed to define the coboundary operator. You need an orientation. You need the ±1 to define the coboundary operator. Okay. So, okay. So as before graphs, we consider faces on the functions on the vertices and functions on the edges. So here we consider function on the I faces. This is the space of, let's say, a space of R-valued I cochains on X. And now we can define the coboundary operator this is the I coboundary operator, which is, what does it do? So for any function on, let's say, the edges, or the I faces, you take an I+1 face and you run over all the I faces in that I plus 1 dimensional phase, and you sum up the value that you get on these I-dimensional phases inside of it, but you need to account to some plus or minus 1, which comes from the ordering or the orientation of the faces. And if I call it the coboundary operator, then what we would like the coboundary operator to satisfy we want this the most basic fundamental identity in algebraic topology. This is not you can check that this is indeed correct, and it wouldn't have been correct unless I put the minus 1, so that's the reason for the orientation. And once we have this, we can define the spaces of coboundaries and cocycles. And because of this equation, the coboundaries are contained in the cocycles, and what you get by quotienting the cocycles by the coboundaries is the space of real cohomology of the complex. And so in some sense there is, maybe this is a good point to kind of, because there will be, I haven't finished with all the notations, but maybe it's a good point to kind of motivate one of the questions that was in some sense responsible for the theory of high-dimensional expanders to even exist. It's a question that Serre asked, and it's related to what we talked about so far in this summer school. So let's say for a complex, a high-dimensional complex, which comes as a finite quotient over Bruhat-Tits building, what can we say about the cohomology? And more precisely, is it true that the real cohomology always vanish? I use D. D is no. There's nowhere. There's no D in this board, right? I want it to be another dimension.
I think there is one D over there.
Ah, yeah, it's good. It's the dimension. Good. So I haven't finished the notation, but I just want to, at this point, kind of connect it. And historically, this question was the question that on which Garland worked, and he was able to prove Serre's conjecture, and in doing so, he gave us one of the most useful tools in the theory of high-dimensional expanders, which we now call the Garland's method, or local to global method. And I want to mention it. I haven't defined what are high-dimensional spectral expanders, but they will be connected to this definition. In fact, if you recall, expanders are always connected. So in high dimension, I want to say that high dimensional expanders are, whatever they are, they should give me some connectivity result. As a consequence of being a high dimensional expander, should be connected. What does it mean to be high dimensional connected? Well, it means that the cohomology should vanish. Okay. So let's continue with the definition. So,
So sorry, then Garland proved that this was true
for all finite quotients, the residue degree should be large enough, but all finite quotients, and yeah, this is
and he showed that's true for all I.
for all I smaller than the dimension. Yeah.
What happens at the dimension?
So you cannot be zero-dimensional trivial cohomology in all dimensions, and so all of the interesting cohomology just push to the top dimension. That's the best you could hope for. Like for graph, one dimension, like the one dimension cohomology of the graph is very large. There are a lot of loops. Okay, so now continue the definition. So there is an inner product on the space of cochains where this weight for any face I assign to it the weight and the degree of sigma, which is the number of maximal faces that contain sigma. So I prefer to normalize the inner product like that. And now let del be the adjoint operator to delta. Just like we've seen before in the graph case, and now we can define the analog of the Laplacian, the high dimensional Laplacian. Well, first before that, note that this operator, you can call the boundary operator, also satisfy this identity, and so we can define the boundaries, which is the image, and the cobound and the cycles, which is the kernel, and the homology. Okay, and now we can finally define the operators on CIX. There will be three operators. In the graph case, there was one Laplacian, but here we have three. Where there is an up Laplacian, where you can first go up and then go down. But because we're in high dimension, we didn't have it for graph. There is a down Laplacian. We don't have it for graph because if you go from functions on the vertices to function on the empty set and then get back, you don't get anything interesting. And finally, you can take the sum of them. What you get if you were to put this on the graph, then you will get the identity operator times the degree. But in high dimensions, we want to consider both of them, to take their sum, and finally, for people who are familiar with differential geometry, there is a space which one might call the space of harmonic on the complex, which is simply the kernel of the Laplacian. Okay, so you see that there is a lot of structure in high dimension, and fortunately, we have the following result due to Ekman, which is a simplicial Hodge decomposition. Which tell us that the entire space of coboundaries, of cochains, I can decompose it to an orthogonal direct sum of the coboundaries, sorry, of the boundaries, the coboundaries, and the harmonics. And not only that, the cycles, which I know they contain the boundaries, also contain as a direct summand of the boundaries the space of harmonics, and same goes for the cocycles. Which in particular tell us that the cohomology space is isomorphic to the homology space, which is isomorphic to the space of harmonics, and therefore, if you want to answer Searle's question, what you really need to do is you basically are reduced to showing that there are no harmonics, that the kernel of the Laplacian is trivial. Okay, so that being said, I can now define. So by the way, this is a simple example. For a graph, for X a graph, I'm interested in dimension 0. I just want to note that if I look at the space of zero cocycle, so in it I see the space of the zero coboundaries, which is just constant functions, nothing more. So if I want to show that, say the cohomology is trivial, and H0 is trivial, which is the same thing as saying that X is connected, it's exactly the same as saying that the minimal spectrum of the Laplacian restricted to the functions orthogonal to the constant function, that this should be strictly bigger than 0. If 0 was an eigenvalue here, meaning that there is, so 0, by definition, 0, any eigenvector with 0 eigenvalue belongs to Z0. And that means that there's some non-trivial element in the harmonics, and we get that the graph are not connected. So this is indeed, might not, it might take a while to absorb this, but this is indeed a generalization to higher dimensions of spectral properties on graphs.
Garland's method was this inner product giving me orthogonalities?
So Garland's method is, I haven't described Garland's method yet. I'm just building up to describe the definition. I mean, there is something to be said about the definition being a bit cumbersome the first time you see it. Garland's method would appear right after I give you the definition of what is a spectral high-dimensional expanders. And his method is spectral. So I will tell you exactly what is his method, but first I just want to finish. Okay, so for any I between d and 0, define the I or the I-dimensional spectral gap to be mu, the I here of x, is the minimum running over all the eigenvalues of the Laplacian once I'm, or the ones orthogonal to bi, because these are truly trivial in an uninteresting way, like the constant function. So all the other ones I want to check what is the minimal spectrum of this operator, and define or say that x is an epsilon spectral expander if I have a spectral gap in all interesting dimensions. And just as a remark, you can, it's the same idea. Okay, so two remarks. Maybe number one, this indeed generalized the notion of spectral expander graphs to higher dimension. And two, I just want to note that when there is no spectral gap, so having no spectral gap happens if, or let me just say that it's the tiniest spectral gap there is, it guarantees that the cohomology dimension, the corresponding dimension is trivial. So what you see is that if you think about vanishing of cohomology as a connectivity property, and a connectivity property, it's a qualitative property. You either have it or you don't. Then this is equivalent to being some spectral gap not uniform, just having this number to be strictly 0. And the notion of a spectral expander is a quantitative statement of this property, which is equivalent to connectivity. Okay. So now we know what are spectral high-dimensional expanders. Next question will be whether we know of any example of spectral high-dimensional expander. How do you prove? And this is where we get to think Garland. So Garland, and then there was Oppenheim contribute an important feature here, so I want to just write the results together to say that if X is a d-dimensional pure simplicial complex satisfying the following local property, that for any face of dimension d minus 2. So if I was a two-dimensional complex, I look at all the vertices, and all these codimension 2 faces, I can look at their links. And what I want is that their spectral graph to be good, really good, not just bigger than epsilon, but bigger than d minus 1 over d plus epsilon. So if our complex is two-dimensional, this should be strictly bigger than half, which is the same half in Indira's talk. It's the same half that Zhuk criteria needs. It's exactly the same tool. The tool is Garland's. And so if this local condition holds, then X is an epsilon spectral expander and it's an epsilon spectral expander. Okay, so this is the famous Garland local to global. And let's see a corollary of it. Let X be the quotient, the finite quotient of what it's building. And let's assume that it has a residue degree large enough. So residue degree, remember, it's the residue degree of the field, the non-Archimedean local field associated to the group to which B is associated, Q, and it should be large enough compared to the degree. Yes?
The question about the theorem, because I read the theorem a few times, and there it's always required that the links of all dimensions are connected.
Yeah, thank you. It's a pure simplicial complex connected. Yeah. Connected.
Connected in this sense, or?
Like the one skeleton is connected. But the one skeleton of all links have to be connected.
Yeah. So I just. So so this theorem so this should be connected also, it's part of the assumption, but here we're going to get it for free. Like the links of Bruhat-Tits buildings are always connected. Yeah. Thank you. This is a good remark. Okay, so if we are a finite quotient of a Bruhat-Tits building, then and the residue degree is large enough, then X is a spectral expander it's an epsilon spectral expander for epsilon which depends on Q and D but not on gamma. So this is the gift that Garland gave us. So just think about it for a minute. What's amazing in this corollary is that you start with some finite quotients.
You need the D to be true. It would be nice otherwise.
Yeah. Yeah. It's everything here. It's a high dimension. I finished talking about the grass in the first part. So think of it like this. So you start with, you take, as Francois told us, there was these arithmetic groups that they could be co-compact lattices of the building. So you take the principal arithmetic one, you divide the building by it, and you get something very small. And now you can take congruent subgroups and these will give you bigger and bigger covers of the Bruhat-Tits building. A cover of the finite quotient of the Bruhat-Tits building. They are all going to be finite. And one. And the remarkable thing is that, so you can ask whether these are expanders, high-dimensional expanders. And the remarkable thing about Garland's method is that to prove that they're expanders, you don't really need to care what are the congruent subgroups at all. You don't need any global information about the object. The only thing you need to know are what are the links and the fact that this is connected. But showing that the underlying graph is connected, that's not how. And the links of all of these are the same. The links, the local structure does not change when you take cover. So you get the spectral expansion of these complexes almost for free by Garland's method. Yeah.
And what was Garland's original result and what's the contribution?
And I forgot, so so this is a corollary, and now the corollary to the corollary, I remove Searle's question, but corollary to the corollary. For under the above assumption, of the residue degree large enough, the real cohomology of all the finite quotients of Bruhat-Tits buildings are trivial. So Garland was able to answer Searle's questions. Yeah, so I think yeah, I will not go into the third thing I expected, but I just want to mention, so this is, so today's talk we basically saw a definition of how to generalize spectral expanders to higher dimensions using this notion of the high dimensional spectral gap, and we showed Garland's remarkable results that, that tells you that if you're locally a good enough expander, then globally you're good enough spectral expander. Tomorrow we will see what will be the high dimensional of the Cheeger constant, and then discuss whether spectral gap implies Cheeger constant with higher dimension, and spoiler, it is not. So we'll see what we can do even when we don't have the Cheeger inequality. Okay, thank you.
Thank you, Shai, for this wonderful lecture. Do you have questions?
Yes.
How effective is the epsilon that you get that depends on
Oh, extremely effective. You see, I didn't say it, but usually the one-dimensional links of a building have the spectral gap, which is, they are the Hilbert graph, the one that, either those or they're complete bipartite graph, so even better. And so this is when Q is the residue degree. This is the spectral gap. So you get to choose. You can increase this large enough so that this is bigger than d minus 1 over d, and then you get your spectral gap. Efficiently, we do, so this is the case where we have a good bounds, and tomorrow there will be terrible bounds.
Other questions?
So what is the structure of these subsequent kind of complexes that you get?
It's a good question. So what is the structure of the LPS graphs? So I know locally they are regular, so I know what they look like locally. Globally, they are hard to draw, and you can tell things about them. And Ori will tell us about beautiful mixing properties and cutoff. But I think that you get to tell that not by geometrically knowing what they are, but by spectrally knowing how good they are as Ramanujan graphs. And here, specifically those ones, when you take congruent subgroups, so this is related to my talk from yesterday, you might be able to show they are Ramanujan, but to tell you how they look like at the very end, they are remarkable, but I don't know how they look like.
Yes?
So the link complexes themselves, they are also high-dimensional numbers?
Yes, the link, they are, the links of, maybe I just want to repeat from Petra's talk, the link of a Bruhat-Tits building is a spherical building, and these will be high-dimensional spectral expanders. They are also high-dimensional cohomological expander in the definition I'll tell you about tomorrow, which is a harder property to achieve. They are missing one thing that I haven't completely stressed in this talk. Usually when we talk about expanders, we want bounded degree. The degree of all the faces should be bounded when the size of the graph goes to infinity. And this is not true for the family of spherical buildings. The degree grows with the number of vertices. So they are excellent expanders, but they are not sparse. So technically, if you were to, they don't qualify as high-dimensional expanders in that sense. Yeah, thanks for the question.
Thanks, Shai, again. And